Before we jump into the topic, let me briefly introduce myself. I'm Oliver. I have like some engineering physics background, so I was focused on aerodynamics, fluid dynamics, and all these kind of things. And the last 10 years, I worked for a small company located in Berlin, which is called SmartPlate. And what we did is we designed these small little aerodynamic add-ons for wind turbines. These are small plastic pieces that you can stick to the blades, and they create these small tiny vortices, air vortices, and they help to improve the performance of wind turbines by an amount of 1 to 3%. And yeah, of course, one has to prove that. And in my professional career, my main responsibilities were to do large-scale studies on large wind farms. We did a lot of experiments with hundreds of turbines, and to get out of data the information how much worse are these little plastic pieces. And in my past, I also looked always on past data. So data was recorded, and I analyzed what happened in the past. And now I found it interesting in DSR to look a bit in the future, to deal with some forecasting things in wind energy. Forecasting is quite a relevant topic. So what happens when you are a wind farm operator? You collect a lot of data. If you have hundreds of turbines, they all deliver a lot of sensors and things like that. And you might use that data to analyze the performance of your machines, or you do failure analysis and things like that. So that's all what you can do on the data that you collected in the past. But what we will discuss today is like what happens in the future. So we will focus on the question, not what happened in the past. We will question what will happen in the future. And when I say future, I might mean the next year or the next month and stuff like that. What we discuss here is like the next day. So my topic is to forecast the power output of a wind farm for the next day. And we have good reasons to choose 1 day period, and this we will see a little bit later. So why is wind power forecasting important anyway? Like in every business that you can imagine, if you have a factory or if you have a restaurant, you will always do some forecasting. You will do some production planning. You will do some resource management and everything. And what makes it very special in wind energy is that you deal with a very stochastic, chaotic environment. So your production planning depends on the weather, and we all know that weather is fluctuating a lot and is really crazy sometimes. And imagine your whole business is based on this crazy weather. So let's have a brief look in the decisions that we have to make when we speak about wind power forecasts. One main thing is that you have machines that are really robust, so they are designed to last 20 years, but they will need maintenance or upgrades and things like that. And when you do these kind of things, you want to shut down the machines, or you have to shut down the machines, and you want to select periods in time where you have low winds and where you don't lose any production when you stop it. This is some problem with the graphs in this setup here, but so what we see here, or what we would see is like some time series of power, and we would identify low wind seasons where we can send these guys, for example, to the machines. We can stop them and they can do their work the whole day, and we wouldn't lose much in production. So that's one important topic. There are many different other things like that. What we call this kind of scenario that we want to do here is downtime reduction. We want to have the machines always running, and we don't want to stop them at all, but sometimes we have to. Another important thing for forecasting is, of course, marketing. So wind energy is an energy that is marketed on the energy market. There are very, very different setups in different countries and different market segments. But one of the most common segments is a day-ahead trading market. And this works as follows. At 12 noon for a specific day, you make a forecast, which we see in blue here, which is your commitment to the market, which states this is a power that I will produce the next day. And when you do this commitment, you get also a price for that and everything. But what will happen in the future on the next day? We have weather that we cannot know exactly, so we will have an imbalance. So our actual production on the next day will be different from that we forecasted. And this difference is a problem for the grid, and the market design is such that you are responsible to balance this out. So when you have an overproduction, you are responsible to sell it on a real-time market, for example. And when you have an underproduction, you have to buy somewhere else some energy to balance it out. And if you don't do your job, you end up in the balancing market. It's another market segment where the grid operators come and do the balancing for you, but you will get a high bill for that. So that's a thing that's quite important. And this area here that we see, that is energy, that's balancing energy that we have to balance out. And it's very tricky to translate this energy to amount of money, because every wind farm operator does specific actions to compensate this. So you might have a storage with some reserves on your own, or you might be very active on a real-time market. However, to put some financial points on it, I did some research, and it's quite different in every country how much this energy costs, this balancing energy. But it's like 1 to 5 euros in the US and 2 to 3 euros in Europe. And what I did here in my experiments, I can easily count the amount of energy here in this graph, so in this area that we see here. And I can take an average price of $2.5 per megawatt hour, and I can calculate the cost that our imbalance is causing. And in this example, that's 1 day of operation, we would have a cost of 883 euros or dollars. I used some data set that I had from a big wind farm in the US, and it's quite a big wind farm. It has like 125 turbines, and it has a rated capacity of approximately 256 megawatts. So it's quite a large wind project, and it's even larger because these turbines here, they also belong to this region, but I did not have any data for that. So I focus on this 125 machines. And the first thing that we can do is build a very, very cheap baseline model. And what you actually do is you take all your data that you have from this wind farm, and you plot them on the x-axis wind speed and on the y-axis power. And immediately you see some relations. When you know the wind speed, you can estimate the power. And what you do is you use like actually these kind of, and what you can do now is you go to some weather service like Deutscher Wetterdienst or NOAA in the US. You get some good weather forecast, which hopefully looks better than this graph here. And then you know, for example, like tomorrow at 9 o'clock, I will have 10 meters per second wind speed. So you go here, 10 meters per second, you check this curve, and you see like, oh, I will expect for this machine 1,760 kilowatts. So this model is really, really cheap. It's easy to do, a couple of lines of code, and you don't need any expense for that. I use that as a baseline. Wanted to do some deep learning, and I wanted to compare like deep learning models. And what I did is implemented something that I found in research papers that was useful also in the past. And these are these typical sequence-to-sequence models with an encoder and a decoder. And what the encoder does here is you put in all this historical time series data from the last 2 or 3 or 4 days of your wind turbines. So you have power, wind speed, wind direction, status codes, a lot of data from the machines. And the encoder squeezes out as much as information as it can from this historical data, encodes it in a certain state, and passes this to the decoder. And the task of the decoder is to generate a new power sequence, which hopefully gives us a good forecast. So that's the core module that I implemented. But this one is, would be still very poor because it only considers a single wind turbine. So you put in a data time series of a single wind turbine, and you predict the power output of a single wind turbine. And you would not use all information that you actually have. We have a whole wind farm. So we have a whole wind farm, and we also have a weather forecasting services. So I did some adaptations on this model that I found. So one adaptation was to add to the encoder part some models that aggregate data from wind turbines in the neighborhood of a specific wind turbine. So when you have a wind turbine located here, you have some wind turbines in the surroundings, and you get some data from that as well, aggregate it, and also pass it to the model. And the second thing that I implemented was some neural networks that take in these weather videos. So you can get for every region a weather forecasting video, which gives you wind speed, temperature, relative humidity, and everything else. And the idea was to run convolutional networks on it to extract relevant features from the weather and to pass it to the decoder and help him to give a good sequence for the future power output. So that's the, compared to the baseline model, more expensive model in terms of effort. But as we will see, it will be worth it also. So here we can see the both models, the sheep baseline model here on top and the deep learning model on the bottom. And we see in blue the predicted power output, and in gray and in the area we see the actual output and the amount of energy that we have to balance out. And what we see here is that, quite often the deep learning model is better, but these are individual points in time, in a couple of days. Sometimes it's even worse than the baseline model. So we cannot generate any information out of that, just a rough feeling how these models look like, what you would see. In order to really bring it to a final value, I did this kind of thing for a complete year. So I did for every day in a complete year in 2020 a forecast and compared the actual data that the wind turbines made with my forecast. And then I computed the amount of balancing costs that you would have for the full year. And this is summed up here, more or less. So it's a relatively large wind farm, which produces a lot of power. So also the balancing cost would be significant, but compared to the overall benefit, there are still small numbers. So what we see for the baseline case, it would be roughly, when we assume 2.5 euro per megawatt hour, we would have a balancing cost of 1.4 million for a complete year. And for the deep learning model, it would be the half, 700,000. We have to be careful with these numbers. As I said, everybody can do trading actions, can have battery stores, and have different mechanisms to deal with balancing. But what it shows is that having a good model for power forecast is quite relevant and significant. And another thing that we see here, which is like the monthly balancing cost that you would have, this is like also quite interesting. The baseline is really poor in the summer. So there's still some seasonality in it, but okay, it's a very cheap model built within a couple of hours, and what would we expect? In the end, it turns out that it's not that cheap because the cost comes afterwards. Yeah, final thoughts and thoughts on future work that I have for this project is to improve the model. There was not enough time to do a decent hyperparameter tuning, and I have also some ideas that I would implement as well. The next most important thing is to make it a probabilistic model. So what you would like to see is not only a single line for a forecast, but you would like to see some uncertainty measure, like how certain is the model. So that would be quite relevant. And of course, deployment and system integration is the final thing that would have to be clarified in this case.